Hey guys, I want to go over the basic principles and concepts behind projectile motion. So projectile motion is going to be a combination of things that we've already been talking about. So going back to like Newton's first law of motion, if we were to launch an object horizontally, like let's say we roll a marble across the table, if there's no gravity, that marble will continue its state of motion. So it will keep moving, same speed, same direction, covering the same space between. Because if it's moving at constant velocity without gravity, this is exactly what the ball would do. It would just keep moving in a straight line path at a constant speed. Now the equation we're going to use is going to be Vx for the x direction equals dx over t. Now what happens vertically? What happens if it falls vertically? Well, as far as vertical motion goes, it's almost like we were dropping it. So if we were to drop the ball, you would see that the ball would actually fall and get greater and greater distances as it fell, due to the fact that gravity is pulling it down. Therefore, we're going to use equations like Vf equals, now I'm not going to put the Viy because that's going to be 0, plus g times t. So vertically, it will increase by say 10, 20, 30, 40, like we did earlier. Also in the y direction, what I want to do is use dy equals 1/2 gt squared, because in the y direction, gravity. Now, when you combine the two together, what happens is when this one here and this one here combine, both the vertical and horizontal, you get your projectile motion. That's where each component, both the x and y components, come together to give the object both its speed and direction of motion. So this is actually the path that the projectile would take. It's a combination of both the horizontal and vertical components of motion. Let's do an example problem. Let's do an example problem of something that was like launched horizontally. So let's say that, let's say you climb this tower, small little tower, 5 meters up high, and you were to toss a ball exactly horizontal, nice and fast. If the ball traveled a distance of 25 meters, can you figure out how fast that ball was thrown up here? Well, first thing we'd want to do is figure out how much time it took for this ball to fall. Well, both, if I was to drop the ball or throw it exactly horizontal, they would both hit the ground at the same time. Therefore, I'm going to figure out how much time it would take the ball to fall 5 meters by using dy equals 1/2 gt squared, which is going to be 1/2 10 t squared. 5 equals, to take half of 10, you have 5 t squared. Divide both sides by 5, take the square root. You'd figure out it's 1 second. So it falls 5 meters in 1 second. Now you can put that back into this equation, because we're trying to figure out what is the initial velocity in the horizontal direction. Well, that would be the 25 meters of distance in the x direction divided by the 1 second it took to fall. So therefore, you'd have to throw this object at 25 meters per second horizontally for it to go 25 meters if you're on a 5 meter tall tower. What about if you throw it really fast? Fastest that you could probably think you could throw. Well, this would be something like Superman. If you were to throw it really, really fast, say 8,000 meters per second or 8 kilometers per second, the Earth, the curvature of the Earth, for every 8,000 meters of distance, it drops 5 meters, all right? So if you were to throw something at 8,000 meters per second, 8 kilometers per second, now that's also 29,000 kilometers per hour, 18,000 miles per hour, it's pretty fast. You would actually, what we say, orbit the Earth. You'd have to be above the Earth's atmosphere. And that's kind of what the International Space Station does. It actually free falls around the Earth. Now let's get to launching something at an angle. So let's say you were to launch something at an angle, like you had a cannon firing a cannonball. Well, without gravity, the ball would just keep going straight in a straight line path, just up and up and up and up and up. Now, every second of fall though, every second that it goes by, it would fall 5 meters in the first second, 20 meters in the second second, and 45 meters in the third second. That's why your objects thrown up at an angle or fired up at an angle follow what we call a parabolic path, a nice parabolic path. To get a really good idea of that, let's take a look at this image here. So over here, this is if we toss an object straight up in the air. This would be your vertical velocities. So you can see that they get smaller and smaller due to gravitational pull. So it would maybe, let's say we toss it up at 20. 20, 10, 0, 10 in the other direction, 20 in the other direction. So you can see also that the vertical is 0 at the top. Horizontally again, the object would be moving at the same exact speed, horizontally. And when you combine together both the vertical and horizontal components, you get this nice parabolic path. Now what we'll be doing with our problems, we'll actually be given our initial angle and our initial velocity here, and we would actually break it down into the x and y components. You'll see that later. One additional note is only at the very top of the path is the vertical velocity 0, but you still have horizontal velocity. And finally, one more big idea with projectile motion is what happens when you fire things same speed at different angles. If they both add up to 90 degrees, they will land in the same spot. So for example, I fire something at 40 degrees, fire something at 50 degrees, same speed, 40 plus 50 is 90, they'd land in the same spot. Obviously, you take 90 degrees and half of that is 45 degrees. So 45 degrees would be the maximum that you can fire a projectile at, maximum at 45 degrees. Hopefully this helped you out with projectile motion.